Hi everyone, my name is Elyse Pennington, and I will be talking about modeling the formation of secondary organic aerosol from volatile chemical products in Los Angeles. Volatile chemical products, or VCPs, are a class of emissions consisting of commonly used consumer and industrial items, as listed here. As vehicles have become cleaner, the emissions from on-road mobile sources have declined, as shown in this time series on the right. During that same period, the emissions from VCPs have increased and become relatively more important as a source of emissions in urban areas. Recently, the VC-Pi framework was developed by Carl Seltzer at EPA to model the emission rates of about 400 individual VCP species. I encourage you to check out his presentation to learn more about VC-Pi and how those emission rates are calculated. After developing the VC-Pi framework to represent the emission rates of the individual VCP species, our goal was to come up with a chemical mechanism to represent the formation of secondary organic aerosol, or SOA, from VCPs. And so our first step, as shown in this figure, was to assign SOA yields to the individual VCP species. Next, we came up with the chemical mechanism that categorized the individual VCPs into 5 general categories, as shown here. The 3 new pathways that we came up with, which I'll describe in more detail in the following slide, are siloxanes, other oxygenated IVOCs, and non-oxygenated IVOCs. The 2 other categories, shown in purple and green, include first traditional SOA precursors, and these are VOCs that are already included in most models. For example, formation of SOA from toluene, VOC alkanes, xylenes, etc. And then the 5th category in green are species that do not form SOA, and these include smaller molecules like ethanol or acetone. Shown here are the 3 new chemical mechanism pathways that we implemented. On the top are siloxanes, and these are a type of oxygenated molecules that serve as a gas phase tracer from personal care products. And siloxanes are treated separately from other oxygenated IVOCs because they have a much slower reaction rate with OH. And so siloxanes use a 2-product model to represent their formation of SOA. Next, we have oxygenated IVOCs, and this uses a relatively simple model with a single gas phase precursor that undergoes a 1-step reaction with OH to form a non-volatile aerosol product with a constant SOA yield. This is a fairly simple model because there has been pretty little laboratory and field data collected about the SOA yields of many oxygenated IVOC precursors to SOA, and so this model could be updated in future as more of that data becomes available. And the rate constant and SOA yield that we used for the oxygenated IVOCs comes from the mass weighted average in LA County of the individual VCP species assigned to these surrogates. And then lastly, on the bottom, we have non-oxygenated IVOCs, and this uses an existing model from Liu et al. That was parameterized using data from mobile source emissions of IVOCs, and we found that the non-oxygenated IVOCs from VCPs had similar structure and properties to those mobile source IVOCs, so we were able to utilize that model. Our next task was to create a speciation profile that would assign the individual VCP species from VC-Pi into the model surrogates. And the mass of those emissions in LA County in 2010 are shown in the outer ring on the right. We see that about equal amounts of emissions are assigned to the new oxygenated IVOC and non-oxygenated IVOC categories, with about 3% of emissions being siloxanes. About 20% is assigned to the traditional SOA precursors that I described before, such as toluene and xylenes. And so in total, about 44% of the VCP mass in LA County is assigned to SOA precursors. In the center ring, then, we have a description of mass that would have previously been discarded in older speciation profiles, but is now utilized in this updated model. So the hatched regions indicate species that in old speciation profiles were assigned to model surrogates that do not undergo model chemistry, and those are listed here. But now we see that that mass is being assigned to chemistry to form SOA using the 3 new model surrogates. We implemented this model into CMAC version 5.3.2 beta to overlap with the CalNext campaign that happened in California in May and June of 2010, and we used the configuration options shown here for our model simulations. Our model results indicate that VCPs form a substantial amount of SOA in Pasadena. Shown in this figure on the left, we have the average diurnal profile of our model simulation results. The green line shows the results from a model run with VCP emissions zeroed out and none of the new VCP chemistry. And then in blue, we have the model results from our case with the updated VCP emissions and chemistry. And we see that SOA is approximately doubled by including VCPs. These are compared to observed PM1 SOA, shown in black, and we do still see an underprediction of SOA, which has historically been the case due to the complexity of modeling SOA formation in these regional scale models. If we now just take the total SOA predicted by the 2 simulation cases, we can subtract them to get the difference shown in the black line, the black dashed line, and understand where that difference is coming from and where the additional SOA is produced. And we see here now on the right that most of the additional SOA is coming from the non-oxygenated IVOC precursors. And as I pointed out a few slides back, non-oxygenated IVOCs and oxygenated IVOCs were emitted in similar amounts, but the non-oxygenated IVOCs form significantly more SOA because of the higher SOA yields of the individual species assigned to these model surrogates. Following the non-oxygenated IVOC SOA, we have SOA formed from traditional species. As I said before, this includes toluenes, xylenes, etc. And lastly, we see negligible SOA formation from siloxanes, and this is due primarily to their very slow reaction rate with OH. The VCP emissions and chemistry updates also improve model representation of other criteria pollutants. Shown in these figures is modeled concentrations versus observed concentrations of SOA on the left, formaldehyde in the center, and MDA8 ozone on the right. And we see that the predictions were improved for all 3 of these species between the 2 simulation cases. We were interested in the improvement in modeled formaldehyde, and so we decided to look a bit more into the relationship between SOA and formaldehyde. Shown here in these figures on the right is the bias, which is calculated as modeled concentrations minus observed concentrations, for SOA on the top and formaldehyde on the bottom, versus temperature, divided into 5 temperature bins. And the zeroed out VCP case is shown in green, while the updated VCP emissions and chemistry case is shown in blue. And we see a similar signature where the bias fluctuates around 0 for lower temperatures, but becomes more negative at higher temperatures. Additionally, we see that between the 2 simulation cases, the green versus blue box and whiskers, we see a greater improvement in predicted concentrations at the higher temperatures for both formaldehyde and SOA. Versus at lower temperatures, we see that predicted concentrations are more similar between the 2 modeled cases. And so we postulate that formaldehyde may be a good species to track in future simulations when looking at the VOC chemistry from VCPs, since formaldehyde is showing such a similar signature as SOA. Especially because we did not see the same signature when we looked at primary organic aerosol, POA, or carbon monoxide, CO. So formaldehyde could be an interesting VOC to track in future work. So to wrap up this discussion on VCP model development, we found that VCPs are an important source of anthropogenic emissions and precursors to SOA formation. They contribute up to half of anthropogenic SOA in Los Angeles in 2010. And because of the similar relationships shown between formaldehyde and SOA with temperature, we believe that formaldehyde and SOA may have common sources and/or chemistry and should be investigated together in future work. And all of this work has been published on ACPD recently, so I encourage you to check out that paper for more information. I'll also touch briefly on a project that we're currently working on to use CMAC to model the formation of SOA and other criteria pollutants in LA during the COVID-19 pandemic. So last year in 2020, in Southern California, we saw large reductions in mobile emissions, but we also had periods of extreme heat and higher than normal rainfall. And the nonlinear interactions of these emissions and meteorology caused different degrees of increased or decreased levels of pollutants in the LA basin. And it was not due solely to vehicular emissions decreasing. And so our goal is to model these changes seen in the LA atmosphere and understand the nonlinear impacts of emissions, meteorology, and chemistry. This diagram summarizes our model setup for this project. We will be using CMAC version 532 with additions of the VCP chemistry that I described in this talk, as well as the mobile IVOC chemistry updates that I mentioned from Liu et al. Our initial boundary conditions will come from GeosChem, which uses scaled anthropogenic emissions according to COVID-19 reductions, and our meteorology is provided by WRF. We have emissions from many sources. So for one, VCP emissions are provided by the latest version of VCPI, version 1.1. We are using on-road mobile emissions from the MFAC 2017 data, and we'll scale those using VMT, or vehicle miles traveled data, specific to the COVID-19 pandemic that will be spatially and temporally resolved. Biogenic emissions are calculated in line in CMAC, and all other emission sources are provided by the CARB emissions inventory. And the modeling domain is shown in this map here. It includes all of LA County along with parts of surrounding counties. Model predictions will be compared to routine monitoring AQS sites throughout the domain, as well as SOA speciation data collected at Caltech and Harvey Mudd College. We will be performing many sensitivity simulations as shown here to understand the contributions to these pollutant concentrations from various emission sources, as well as aiming to understand the impact of meteorology and different chemical processes. Finally, I would like to thank these contributors and funding sources, and thank you for listening, and I'm happy to take any questions during the Q&A. Thank you.